also, it's a particular interest of mine. I have followed the spread of infectious diseases over the globe, and prevention of infectious diseases is significantly helped by networks. What you are going to hear about is other disasters that can be predicted or perhaps alleviated by the effect of those disasters can be alleviated by technology. We have a mini problem, and that is that we don't have one of our speakers. Let's see, Jose Luis Goberna Caride is not available. He has not shown up. He's missing in action. He's a member of the Spanish military, and I hope there has not been some problem that we don't know about in sunny Malaga. So our two speakers will have the opportunity to speak a little longer, if they are able to do so. So our first speaker is from Hawaii. His name is Chris Chiesa, and he's the Deputy Executive Director and Chief Information Officer at the Pacific Disaster Center. Chris.
Thank you, Jacqueline, and buenas tardes. I don't know, I'm going to start with a little interactive part of our session today. I don't know if any of you have had the opportunity to visit Hawaii and be there for any kinds of meetings or conferences, but you probably all know the word aloha. It means hello or welcome. It also means goodbye. We always start meetings by saying aloha, and then the audience repeats back. So we're going to see how good of an audience you are. I'm going to say aloha. Aloha. Okay, very good. Thank you. Although my title is Chief Information Officer, I'm pretty sure that I'm outmatched in terms of network and overall IT skills and capabilities. I'm going to focus, I guess appropriately so in this session, on user applications in terms of some of the content that we provide, content and analytical functionality that we provide to some of our partners in the disaster management area. And I'm going to focus on one of our latest applications, which is the global edition of our Natural Hazards and Vulnerability Atlas. I'll describe a little bit, actually let me advance to the next slide. A couple of slides on the Pacific Disaster Center, just to provide a little bit of context. And then share with you some of the disaster management challenges that we see, at least from an information technology perspective. And then some of our solutions, including our Disaster Atlas, Hazard and Vulnerability Atlas. And I'll end, I think, with a slide or two on how we've also customized that general purpose or publicly accessible atlas, how we've customized that for use by national disaster management agencies in Asia as well as in the US. And since there may be a little bit of time, I do have the atlas, which is internet accessible, of course. I have that loaded, and we can maybe take a look at what's actually going on in the world right now. This is literally our mission statement, and a couple of words are highlighted. Again, often in a venue of other disaster managers, not so much other IT practitioners. So one of the things that we really stress when we talk to our colleagues and collaborators is that even though we're affiliated with the University of Hawaii, we're not a traditional academic organization. We really do applied information research and applied information technology that supports some of the operational needs of our colleagues, that is disaster managers and agencies that provide humanitarian assistance after disasters. As our name suggests, Pacific Disaster Center, and our location in Hawaii suggests, We are very active in the Asia-Pacific region. However, the grant that we receive from the U.S. government that provides maybe 3/4 or 80% of our funding, even in that language, it suggests that we operate in the Asia-Pacific region and beyond. So one of the reasons that and beyond in our case has extended into Latin America, Africa, and as well as some global initiatives. And so one of the reasons that I am here and been happy to interact with the other participants here and looking forward to hearing some of the other presentations is in fact to expand our network of information providers and sort of distribution channels, if you will, for some of the alerts and advisories that we publish and provide. We're active in a variety of hazards, whether it's tsunamis or landslides or hurricanes or wildfires, as are pictured here. As has been mentioned, we are located in Hawaii. For those people that have visited Hawaii, was talking with some of the people at the reception last night who have visited Honolulu or Oahu. We're on one of the neighboring islands. We're on Maui. Our headquarters is actually in a research and technology center. One of the other tenants in that center is a high-performance computing center that's run by the U.S. Air Force. On top of Maui, it's about just over 10,000 feet, is an observatory that is used to track space debris. And the high-performance computing center down in the tech park processes that information that's collected by the telescopes at the top of the mountain, and we kind of ride on their shoulders, both in the IT and computing sense. We also have presence on Oahu, on the main island of Hawaii, or the state of Hawaii, both at the State Emergency Operations Center. So again, if you visited Honolulu, you've seen Diamond Head Crater. It's a very visible landmark. Drilled into the side of that extinct volcano is an emergency operations center, completely in a tunnel with backup power and communications, decision support applications. We have people there, as well as over on Fort Shafter, which is where the U.S. Army Corps of Engineers is located. And in the United States, the Corps of Engineers provides support to civil disaster managers during national emergencies. They often provide logistical support, backup power, food, water. It's also where FEMA, or the U.S. Federal Emergency Management Agency, has a regional presence. So we have staff there that supports those operations. This slide and the next slide, and I think those are the last two slides on Pacific Disaster Center, but this slide really, I think, characterizes what we do, or kind of at the highest level what our mission is as a relatively small, we're about 35 or 40 people, so we don't provide, except in extreme cases, we don't send people out in disaster impact areas, and we're not a federal U.S. agency that has a mandate. We're not the Weather Service, for example. We don't provide the weather forecast. We sort of value add it. But what we really do is help provide a bridge between the science and technology community that's extremely well represented today and the decision-making community that represents either disaster managers, elected officials, governors or mayors of affected areas, agency leads, whether it's, like I mentioned, the Corps of Engineers. They may have to provide logistical support, so they need information on what is needed and where and so forth. And the point of this slide that I think most of you can probably appreciate is that they're very different communities. So the science community, in fact, the plenary presentations today showed temperature curves, and they showed uncertainty bands associated with those temperature rise models. And I think that was a good lead into this. you know, working with, in this community, peer-reviewed processes. Low, comfort with uncertainty, low, really means a lot of analysis goes into the error, understanding the error, minimizing the error, waiting until that error is at a certain threshold before releasing the data, releasing the publication. Very complex ideas, complex vocabularies, very technical audiences, again, well represented today. On the other side, imagine those disaster managers or elected officials, mayors, governors, presidents. They need to interact very publicly with the public very quickly, and they need to make decisions whether all of the information is in or not, or whether all of the information is understood. Sometimes, of course, that means their first action or reaction may later have to be revised as more information comes in, but they can't wait and say, well, I'm not really sure what's happening. Let me wait until all of the data come in, and then I'll decide whether or not there really is a hurricane or I really need to evacuate people. Well, as cases sometimes point out, that delay results in loss of life and loss of property unnecessarily. So if that's sort of what we do, this next slide really talks about how we do it. We are an applied science and technology center, as I mentioned. We work with observational systems, a lot of satellite-based observation systems, as well as in situ gauges, tide gauges, seismic monitoring networks. We don't own those. We work with national agencies and international groups that do, UN or other regional bodies. We don't necessarily develop models, but we have a lot of expertise in applying those models. Often those models or algorithms attempt to translate some kind of physical property or physical phenomenon into consequences. So for example, when we have an earthquake and the ground shakes with a certain acceleration, that's a physical property or physical process. We try to translate that into consequence, meaning how many buildings will be collapsed, how many people may be rendered homeless, how many shelters, food, water, how many rescue supplies, which bridges are likely to be out. So how might I have to route transportation differently, temporarily and longer term? Most of the information that we receive comes in, as I mentioned, we don't own the instrument, so it comes in over some kind of communication system, typically internet, although as we work with disaster managers that are deployed in hazard zones, often it's the commercial communications network has been temporarily disrupted, so we need to use things like satellite communications. Virtually everything that we do has some kind of coordinate system, or geocoordinate or geospatial aspect to it. So we use a lot of GIS and scientific visualization tools for geospatial data. But our real focus is bringing all of those technologies together in a way that disaster managers and other decision makers can more effectively make decisions. So that's kind of what we do. Why is that difficult, or what are the challenges that we face? In spite of all of the advances in technology and communication systems, computing systems, it's still very difficult. There's a lot of information that's received in a very short period of time during disasters, comes from different sources, comes in different formats. Even if you are a native speaker and reader of English, as am I, that's difficult to decipher exactly what that means. Probably the first, and that's an actual bulletin that goes to disaster managers. It's got a lot of information in it, but doesn't necessarily tell you how to act or how to react. It's just sort of a piece of data, if you will. For hurricanes. For tsunamis, similar, but again, different format, different content. Earthquakes, volcanoes. So disaster managers just in our state alone in Hawaii face all of these different disasters. And again, this information is coming from different sources, different formats, different terminologies, different contexts. Not only is it scattered information and so forth in different sources, but generally speaking, there's no risk context. It just says this event's happening. The wind is going this fast at this location and is expected, that location is expected to move over time. The eye of the hurricane is expected to move over time. Is that good, bad? Do I need to make a decision? Well, the National Weather Service, and we're really grateful that they exist, and most countries have some kind of a hydromet service. In the U.S., our National Weather Service does a great job of forecasting hurricanes, but that's really where their job ends. That's kind of where our job starts, is to take that information and turn it into actionable information. This information can be kind of manually read and manually interpreted, but it takes time, and time translates into life in our business, our line of work. Information that you can't understand. It might be highly interpretable to some people, but perhaps not to others. And so I don't know if there's anybody here that reads Korean. I don't. But I thought that was kind of interesting. And even my Korean guests or colleagues at the time also agreed. So we can call that information, but I don't think anybody here, myself included, knows what that means. So again, our job is to translate bits and bytes of data into interpretable, actionable information. Specifically, what we do is work out arrangements with these different providers to receive their messages and develop automated routines to process those, and automated routines to monitor those automated routines to make sure that they're up and running 24 hours a day. Put those into our enterprise services. Often those data get processed by different GIS applications and different analytical models, as I mentioned. With the earthquake, we have similar models that look at wind speed and translate that into whether buildings will be damaged or the roofs will blow off the buildings. We put that into some kind of a decision support tool, one that we've developed at PDC we call Disaster Aware. But there are many, many examples of those systems, and we work with, we provide web-based services into other decision support tools besides ours. And then, of course, make that available to decision makers. And in this case, one of our applications is even available to the general public via what we call our Atlas, Hazards Atlas. We also have capabilities to disseminate warnings, not typically publicly, but to our disaster management counterparts via SMS and pagers and faxes and so forth. So let's walk through an example. This is a real data snapshot from several years ago. Periodically, I update this. The pictures always look the same. I mean, almost any day you go to our Atlas, very, very similar information in it, just different situations, and you'll see what I mean in a second. So here's a hurricane advisory that's coming from something called the Joint Typhoon Warning Center in Honolulu. It's got information about where the hurricane currently is and what its wind strengths are and where it's heading. First step we do is try to take this information, automatically ingest it, and sort of simplify the presentation of it by putting, the first thing a disaster manager would have done pre-automation is go with their grease pencil up to their big wall maps and put an X on the map. So we do that automatically, electronically. I know I'm supposed to talk in here, but just pointing out where the hurricane currently is and where it has been. So that's its previous location. We can integrate that with all of the other things that are going on in that part of the world at that time. So we see a pattern of earthquakes. Those are best illustrated by those string of earthquakes along the Aleutian Peninsula. So we see the green dots in different numbers. We see wildfires across China and Australia. I see some from here. And the triangles represent active volcanoes, or volcanoes that are in some state of activity or restlessness. We can plot that against statistical or probabilistic information. In this case, in blue, looking at maximum likely intensities of storms, and in the green and orange and red, maximum likely intensities of earthquakes. So we can look at real events, so we can look at them in some kind of risk context, what's happened there previously. Is it likely that the population has had some previous exposure to this magnitude of event or not? Or is this something that is really going to catch people by surprise? Zooming in, we see a typhoon off the coast of the Philippines. Again, the circles represent where it is and the distance out to which certain wind speeds are being felt. And we see the path that it's forecast to go along. Of course, as this morning's plot showed, there's some uncertainty with any kind of projection. So we show a 3-day and then a 5-day uncertainty envelope based on algorithms or formulas from the Weather Service. We can combine that with other information. Where are the roads? Where are the airports? In case of the airports, what is their operational status? We've got models, in this case a relatively simplistic model, but it does take the forecasted wind speed and it compares that with different types of structures in terms of whether they would expect severe or moderate level of damage. I think we're showing here a category against a residential construction type category. We can show that in relationship with population density. So we can see, for example, that while this storm is forecast to go over some relatively dense populations, it's by and large going to miss the highest concentration of population in Metro Manila. We can lay those shapes, those polygons, over using GIS, Geographic Information Systems, and get a summary of how many people or how many homes or how many airports are in different hazard bands, providing some indication just even well before the storm arrives at what the level of disruption might be to the society, to the economy, to people's lives, to transportation. Those examples were, these examples, if you notice in the top banner, came from something that was called our Asia Pacific Natural Hazards and Vulnerability Atlas. We've had that application for the last 4 or 5 years. As our mission has expanded globally, we've expanded that application globally. So here we see a snapshot of our Global Hazards Atlas that was launched earlier this year, launched in about January, late January. It tracks a number of natural hazards globally: tropical storms, wildfires, earthquakes, tsunamis, and volcanoes are presently in there. You see the word floods is in italics. We are in the process of including flood information from one provider called the Dartmouth Flood Observatory at Dartmouth College. We also have risk exposure information, as I've illustrated a little bit in the previous slides, where people are, where some of the critical infrastructure is, facilities, other types of critical or important facilities, nuclear plants, power plants, for example, large hydroelectric dams, and other critical assets. The URL, by the way, is listed down there, atlas.pdc.org. That will take you to a launch page that will let you launch either the Global Atlas or the Asia Pacific Atlas, or even a high-resolution version that we've put together for the state of Hawaii, called the Hawaii edition of the Hazards Atlas. No password required. Just a quick appreciation for some of the information. I won't, this is posted online, so I won't go through all of the detail. But just to point out that for most of these hazards, we have both current or active as well as historical. So not only can I see what tropical storms are active at any given time, and I looked a few minutes ago, I guess for good or bad, there are no active hurricanes right now, so I can't show you that. But I could show you a historical history dating back to the 1940s and captured in intervals of sort of 6 hours. So most storms last 5, 6, 7 days, so maybe we've got several dozen points along its path, and we capture how strong it was in those intervals. This is just a snapshot similar to what you saw before. This actually was taken earlier this year. Typhoon Chanhome, I think that was either the first or second named typhoon in the Western Pacific, second typhoon. It did actually go over the Philippines, caused extensive landslides, some loss of life. Again, we see the model that shows damage due to residential type structures or likely damage due to residential structures. Earthquakes, we work with the USGS, and although it's called it is the National Earthquake Information Center, it really works with its counterparts in other countries, and it has access to the whole international seismic network. So it's not just U.S. national, it really is international. That's kind of a conservative estimate every 30 minutes. We harvest from that site about every 10 minutes. Sometimes it takes a few minutes for an earthquake to register with it. So typically, I mean, in as few as 10 minutes, as few as a few minutes really, but maybe as much as 15 or 20 minutes from the time an earthquake happens, the site is populated. Again, we have historical information from NOAA's National Geophysical Data Center in Boulder, Colorado, that tracks large significant earthquakes, 10 or more deaths, or magnitude 7.5 or greater, not through instruments, of course, but through written record or other types of reports going back, well, almost 4,000 years, or over 4,000 years. So we see, again, a snapshot taken earlier this year. At any given time, we show a 48-hour window. So these earthquakes have happened within the last 48 hours. Many of them relatively small, but I see a 5.5 in Central Asia and a 5.1 down in the South Pacific. Zooming in on one of those off the Philippines, we also harvest a ground acceleration product from USGS. It's run automatically. It's called their Shakemap. So not only do we get the earthquake epicenter, and you can see the aftershocks. So 5.9, and then some aftershocks ranging from 4.6 to 5.7, and we can see peak ground acceleration, and it's then mapped into kind of a consequence scale, modified Mercalli index. And you see the legend down in the right indicating that, I don't know my reading glasses, indicating that it's got modified Mercalli values of around 6.5 to 7.5. And that those values, those MMI values, translate into observable or human observable effects. So for example, at a level 5, it might be that dishes might be observed to fall off the table or, out of the cupboard. At level 9 or 10, severe distortion to road surfaces, for instance. And so that's kind of a consequence or observable impact based on not only the magnitude, but the depth and the type of geology. Okay. Similarly, wildfire information, recent and somewhat historical, not quite the duration of other events, but using satellite imagery, thermal satellite imagery to detect large thermal anomalies. We do screen out volcanoes and known industrial processes that also present a thermal signature. Looking at active hazards or active fires in the yellow flame symbol in northern Australia. But this is the fire pattern for the last 8 years or so. Looking at Western Australia, lots of relatively small but observable fires. We also bring in other information that's more human reported. So there's a counterpart organization of ours called the Asian Disaster Reduction Center in Kobe, Japan, and they publish something called a GLIDE number, Global Identifier Number, so that each large disaster event gets tagged with a unique ID, and then UN organizations and other data providers all code using that same ID. We automatically grab their published information and post that. There's also something called the International Charter for Space and Major Disasters. All of the space nations, US, Canada, India, France, European Union, China, have agreed to provide imagery, satellite imagery at no cost under certain conditions during disaster events. So as that gets activated, we also bring in that information. So here we're seeing some of the recent charter activations and GLIDE numbers superimposed on a population density map. And last but not least, but tying into some of the comments that Jacqueline made, although this started off primarily looking at natural meteorological or geophysical hazard, we also have brought in, at the request of some of our colleagues and collaborators, information on avian flu cases and H1N1 or swine flu, pulling data from the World Health Organization and the U.S. Centers for Disease Control. This was a snapshot not too long ago showing some of the cases in North America reported to the centroids of the state. So in this case, we don't have precise geo-coordinates for the cases, as was suggested this morning in one of the presentations. Medical case information, confidentiality of patient records. So as this was reported by each of the state medical boards, we then identified it to the center of the state, but not really to a neighborhood level or city level even, for example. There's some avian influenza cases as well. 2 slides and then I'll finish, just to point out that those tools that I showed you, or those graphics or screen snapshots, that's all from a publicly accessible tool. You can log into atlas.pdc.org and try it yourself. We've used those same processes to develop tools that have gone into national centers, in this case, the National Disaster Warning Center in Thailand, in Bangkok, Thailand. Not only does it have the map information, most of that looks similar, but it also has a window here, a frame here, that allows the disaster managers to create and post information for each event. So this could be situation reports, ground photographs, damage assessment information, or requests for deployment of logistics or relief supplies. And this application, as is a similar version for the State of Hawaii Disaster Manager, is password protected and it's role-based, so different organizations have ability to post and share certain types of information, or can narrow the distribution to only selected users or selected agencies. But the map information is by and large the same information coming from the same processes. So in summary, what we attempt to do at PDC is support our disaster management colleagues, and help to not reduce disasters, but reduce their impacts by making it easier to access and share and understand information. Put that in a risk context, so it's not just information, but we can start to understand whether on a scale, is this a large event or perhaps a moderate event? And then provide warning information to those people that are charged with or have the authority to issue evacuations or provide response. Oops, I thought I had I guess that was my last slide. Thought I had a contact information slide. I will be here for the rest of this session and the session that follows, and I've got a little bit of literature on the back table when you walk in. Feel free to collect some of that as well. And I don't know if you wanted to field questions now or later.
Thank you, Chris.
Thank you.
Are there any questions, Chris?
Oh,
Take them, please, at your pleasure.
I think.
Well, thank you for this. Thank you for this interesting presentation. So you produced a very useful and powerful tool, and it looks like a very critical application. So something that comes to mind is that your own facilities could be hit by an earthquake or typhoon. So how do you make sure that this system keeps running whatever happens? And this information continues.
Good question. So the question really, I don't know if everybody could hear, but talked about reliability of service or redundancy of service. And at present, we do have these services running in 2 of our offices in Hawaii. So at least we're on separate islands. But of course, Hawaii, it would be unlikely realistically, but it could actually be that both islands are hit or disrupted by some kind of telecommunications problem. We do have backup power and we do have redundant communication circuits, but we could be ground zero for some major event. So we are actually looking at taking an instance of this and also running it at a data center on the U.S. mainland. But at present, it runs on two distinct islands with separate and redundant comms and power. Thank you. I think there was a question here. I will mention, by the way, that we had an earthquake that disrupted the power, and we have backup generators that run for 72 hours. The power came back on in about 24 hours, but it automatically kicks in as soon as it notices that it's not receiving commercial power. So we were up, and ironically, we were up and running during the entire event, but one of the emergency operations centers, their generator failed, so they didn't have power to consume our product. But anyway, yeah.
I want to elaborate also on this question because actually I'm involved in creating infrastructures. And so I would like to have a comment on what this means for the infrastructure, because I understood that essentially the data flow is one of the key issues. Mm-hmm. If you're not able to receive data, then you're not able to take decisions. So that is my first question. Okay. And then if I'm allowed the second one. The second one is, you have listed a certain set of disasters, yes, but not everything that may happen. For example, a complete power failure everywhere, mm-hmm, or oil spills. Mm. So do you see categories, or do you see some kind of a taxonomy in disasters so that every of them has to be treated differently, or is just a matter of enlarging a basic set of procedures?
Let me start with your second question first, if I can, and then I'll address the first one after that. So is there a taxonomy? We actually have gone through some effort to kind of look at different types of disasters, again, whether they're geophysical or meteorological or climatic or climatological or human-induced, which could be accidents, could be terrorism. So in this particular application, the focus mostly is on natural hazards, but you saw some well, let's call them public health types of hazards with influenza. With the version, I'm just going to back up 2 slides, the version of tool that we've developed here, in fact, tracks an oil tanker spill. Now this is simulated, but how is that? Well, there's not a global monitoring system for oil tanker spills, but of course, as soon as they're received by the press, we have the ability in this tool, because again, this operates in an emergency operations center, for an operator or an online analyst to be able to mark that and say, there's a hazard here. And if you look carefully, it may be a little hard to discern. Looks kind of like a person standing there. So the symbol is a man-made hazard. It means man-made. Oil spill. And if I clicked on that, it would have brought up links to some of the news reports and some photographs, and of course, and it was simulated, so we had some simulated Coast Guard reports. So that's kind of how we handle other hazards at that level, is we do allow for a manual declaration of it. The other part of that question, I think, had to do maybe kind of with severity or consequence. And we do treat, there's an event, an earthquake happens, the ground shakes, maybe that's not a hazard. Maybe it's not just based, in fact, typically it's not just based on the magnitude of the earthquake, but that's a big component of it, but it's also proximity to people and the intersection of that, let's say in building codes, building standards, building integrity. And so to the extent that we have that information and we don't have it uniformly around the globe, but in areas that we do a lot of work, we have a better inventory of buildings, for example, then we can do a better job of turning a physical event into some kind of hazard level or alerting level, and we do have sort of warnings and advisory level of categorization. Your first question had to do with flow of information, and you're absolutely right. If in the end, for whatever reason, we stopped receiving inputs, but we have dedicated circuitry and dedicated computers at some of our partner agencies, but if we no longer received earthquake information or tsunami information in a timely fashion, then it obviously makes this information, or makes this tool less valuable. But again, we do have processes to if somebody calls us and says, hey, for whatever reason our information feed stopped, but there's been a tsunami and here's the parameters, in most cases we can manually input the parameters that we would have received, and you'll still get the dot on the map, so to speak, plus we'll manually run the consequence model, and that will feed in. So we do have some opportunities to sort of human in the loop if the automated procedures go down for any particular reason. Looks like you've got another question. Or
rather than a question, as a comment.
Sure.
Is there a way to assess the risk of a failure of the transmission infrastructure? I mean, do you assess that risk by itself? I mean, because it's not easy for me to understand how to assess if the infrastructure or the tools that I have there are good enough. Do you have anything?
Right now we're working with, so again, if I understand, it's sort of the a priori likelihood of some part of the system to fail. right now we're working with one of the U.S. Energy laboratories to in fact do that type of assessment, consequence assessment for critical nodes in the power grid. And that's kind of going to be a first attempt, honestly, at looking at that type of sort of logical sequencing of one component fails and then what's the consequence of that downstream, so to speak. But right now, this application more looks at things in a somewhat isolated, or at least not secondary, tertiary effects. Yeah, good point.
One more question?
You mentioned lots of sources providing you sometimes almost online information for the system. Is it difficult to obtain this source of information? I mean, access to this data, because I believe that most of this is not publicly available. So do you have to use governmental or local authorities support to get hold of this data?
Yeah. So the question had to do with access of the data, and do we have to have use our government relationship to get some of the data? Everything in the in these public applications, not the one I'm pointing to now, because that's an application developed for the Thai government, but in our public applications, everything is actually publicly accessible one way or the other. Now, we have data sharing agreements to maybe allow us to republish that information or to get it more reliably, for example. But everything in there is actually available publicly. Now, some of our password protected applications for the government of Thailand, for the state of Hawaii, for other partners, contains information that isn't publicly accessible, and that's fundamentally why it's password protected. In other cases, again, there's sort of some value-added processes that go in, but the core data set itself, the location of that earthquake, the location of the storm current position, those are all available one way or the other via public sources, but one of the value adds is actually bringing it all together into a comprehensive application. I sense I'm out of time.
I just don't want to shortchange our
Yeah.
next speaker, so thank you very much,
yeah.
Chris.
I'm happy to, thank you.
And there'll be many opportunities.
Happy to engage during lunch and
Exactly.
other discussions, yeah.
Thank you very much, Chris. Our next speaker is actually from our home institution here in Malaga. And I'm going to misspeak your name, but I'll do my best. Manuel Jesus Castro Diaz.
Sounds like Spanish.
Thank you very much.
Sorry, I would change the laptop because I have some problem with the plugin.
Tell you that he's a prize-winning mathematician. Victoriano is very proud of him.
have some problem with. Okay. That's it. So, good afternoon. My name is Manuel Castro. I came from the University of Malaga. And this talk focuses on mathematical modeling. So in the previous talk, we have seen that in this kind of tools, there are sometimes the necessity of using some mathematical modeling trying to simulate some physical phenomena. So in this talk, what we are going to see is a recent work of tsunami modeling. Well, one kind of tsunami simulation and modeling. So if I could define our work in our research team, would say that we are model makers. So we develop numerical algorithms and mathematical modeling and try to simulate some phenomena related with geophysical flows. So this is the main core of this talk. In fact, this problem was posed by our colleagues in the Spanish Institute of Oceanography, and they were interested to study the distribution of sediment around the line, the coastal line, and try to investigate the stability of these sediments and how did sediment could produce by landslides some kind of tsunami. So this kind of model could be used to evaluate a zone of risks produced by this kind of tsunamis. In fact, we also developed some other models related with floods, coastal and river flows, spill, all motions, etc. So this is the kind of problem that we are interested in to simulate. So, sorry. The plan of the speech is the following one. First, we do to present our team. Then a few words about tsunami generation. A few slides of the mathematical model that we use. We have developed this particular model. Some numerical examples. And then an utility, a web platform that we use to transmit this kind of numerical issues to our colleagues in order that they could use our numerical tools using a simple web tool. So our team is a really young team. It's founded by Professor Antonio Valle 20 years ago. Now it's directly by Professor Paredes. And the research team is that one. So we have 6 researchers, say junior, senior, and 3 PhD students. As I told you before, our research area, as we are all mathematicians, okay, we focus mainly on the numerical analysis of partial differential equation. In fact, we work on developing numerical schemes based on 5-volume and 5-element method, image generation, and also some visualization tools. But in particular, we focus on this kind of geophysical problems, geophysical flows, so floods, river coastal flows, sediments transport, debris fluids, turbidity currents, tsunami generation, etc. But if we are interested to use this kind of models to evaluate big areas, those algorithms must be implemented in a high-performance way. So we use parallel implementation using domain decomposition techniques. And now we have some prototype working on GPUs. And in fact, this really, really surprising. The reduce of CPU time with this kind of implementation is really wonderful. In fact, for real problems, now we could say that we could really provide really real-time simulation for big problems. Now we have lots of external collaboration. So the main one perhaps is the group directed by Professor García del Río of the Spanish Institute of Oceanography. This is a group of geologists. Then we have collaboration with other mathematical teams. The one directed by Professor Fernández Nieto of the University of Sevilla. Some engineers in Italy, also Professor Randy Levesque of the University of Washington, and also some people from the computational engineering from the University of La Coruña and University of Granada. In fact, those are developing these GPU implementations. So a few words about how a tsunami develops. So what we have is we have a suddenly change of the bottom, mainly the bottom topography. It could be produced by earthquake, landslide, or something, or a submarine volcano eruption. So we have a modification of this bottom topography. Then what we have in deep water is a wavelength of 10 of kilometers, and the amplitude is not very big, say less than 1 meter usually. But when this wave is coming into the line coast, then the wave amplitude is reduced dramatically. So in that case, we have, well, 1, 2, or 3 kilometers, and the wave amplitude increase also big. And we have this kind of wave approaching to the coastal line. So this is roughly the mechanism of propagating this wave. So in comparison with wind waves, so here we have wind wave, we have the wave amplitude of 4 meters and the wavelength of, well, a few meters long, but the tsunami in deep ocean is about that size. The wavelength and amplitude, this is the speed, median speed, and when it's approaching to the shoreline. So different mechanisms to produce tsunami. So earthquakes, underwater earthquakes, submarine volcano eruption, and the one we try to model is that one. So tsunamis produced by landslides, submarine or coastal landslides. And most of them, we could say, when we talk with oceanographers, that this kind of waves are classified as shallow water waves. That means that the wave height are very small in comparison with the wavelength. So we say that from the mathematical and physical point of view, we could manage with this kind of phenomena if we use shallow water models, of this kind of model. In fact, this is the model that we propose to use, and this is the model that we have developed. So it's a model that tries to simulate this kind of tsunamis. So a few words about the model. So this is a recent paper that we have published where we present the derivation of this PD system of equation and also a numerical scheme to solve them. So we suppose that we have water and some granular material. So we suppose that viscosity is not really relevant, at least in the fluid part. For the horizontal viscosity, we keep some vertical viscosity terms. Then we suppose that the density is more or less homogeneous. So, okay, in the fluid is more or less okay, but in sediments it's not really true. But we could try to model the mean evolution of this kind of sediment. So we suppose that we have also a porous media, and then we suppose that both materials are not miscible, so they are miscible. And we suppose that we could manage in the shallow water framework. So this is a sketch trying to describe all the variables. So here we have the water depth, the sediment depth, and this is a bottom non-erodible bottom topography. And this is the free surface. So we are going to try to describe a PDE system of equation, try to describe this sediment evolution under water waves, all together, okay? We put it all together. And at the end, what we have, well, this is a simplified system, okay? This is a 1D system. It's not the system that we use to simulate the 2D problem. But in fact, here we see all the main ingredients. So what we have is a PDE system that models this kind of phenomena. The unknowns are the water depth, the sediment depth. They change on time. And then we have some equation modeling taking into account the momentum conservation from the water layer and the sediment layer. So those are related with the mean velocity and the water depth. So this is a, say, complicated PD system, nonlinear PD system, a hyperbolic. So this system depends on some kind of parameters taking into account the physics of the problem. So we have, for example, here the ratio of densities, this term taking into account the anisotropy in the sediment layer, some friction laws, and this term is quite important. In fact, it's the one related to the Coulomb friction term. In fact, this term is the main one to model the stop of the landslide. Okay, so we have a material that's running down in a slope, and then there are forces that keeping this material, okay, in this bottom topography, in this term. In fact, this term is also difficult to manage with because it's not really an equality, it's an inequality. So this is not really, sorry? Okay, at the end.
Just to understand.
Yes.
I think that what you mean by this dates back to my university.
Okay, sorry, if I...
No, just to understand, because I would like to understand. Essentially, you are saying that you're trying to have a set of equations
Yes.
in which you want to understand as a function the height of the water, and the height of the sediment.
That's it.
But then you have a system
Yes.
which is not just as two variables.
No. It's
The height of the water and the height of the sediments are the
So,
variables, essentially.
not
What you want to
really.
understand.
Also, but you know, we have the height, the depth of the water layer, the depth of the sediment, and then those are related. So with the velocity of the
Fine.
movements. Okay.
Fine, so you have also velocity. Then it solves
that's
my
it.
question, because then you have a system
Of four
dealing with-
equations and four unknowns. That's it.
Okay, so the fourth one is the two heights,
The two
water,
heights and the two
sediments,
velocities.
and the two velocities.
And the two velocities.
Now I understand. Thanks.
Okay, those are related to the mass conservation and momentum conservation principles. Okay, so we write down the physics, we integrate, and we obtain this partial differential equation. So, okay, we rewrite and manipulate in a mathematical way the system in order to derive this this kind of formulation. From the mathematical point of view, this system is quite interesting because we have here some flux function that is related to conserved principles, but then here we have some terms that are very interesting when we have coupled things. And here we couple things. We couple the larger sediment movement and the water sediment. So from the mathematical point of view, these terms are difficult to deal with, and also for the numerical point of view. So let me say that it's critical to represent quite well this kind of coupling things, because if not, the weight speed propagation is completely wrong, and the position of the sediment evolution is also a mistake, you know. So the mathematical representation of the weight speed, the speed of the waves in this problem is critical in order to simulate that in a proper way. So this is the kind of numerical scheme that we use, and in fact we are able to prove from the mathematical point of view that these waves are correctly represented. So let's say that we could be sure, at least from the mathematical point of view, this is a model. So at the end, this is a simplification of real things. But at least from the mathematical point of view, we sure that the wave, the velocity of the wave, so the tsunami wave, when we arrive to the coastal line, is, from the mathematical point of view, correct. So the type of numerical scheme that we use is of that kind. It's a row-based scheme. You could see in the literature what that means. But the idea is quite simple. The idea is what we have computational cells. So it means triangles or whatever you want. And then we describe the physical quantities in these cells, and we manage with this boundary of the cells, and we try to transmit physical principles like mass, momentum, energy. So at the end, the numerical scheme is physically preserving all these quantities. So this is the potentiality of this kind of numerical scheme. So at the end of the technical part, the mathematical part. So let me see a few simulations. So first things that we have done is try to be sure that all the simulations are mesh independent. And this is not always trivial. If you have a really complicated problem, if you change a mesh, perhaps the solution is different. What that means is the numerical scheme is not good enough, because it depends on the spatial configuration of the mesh. So first thing that we have done is to check that this kind of numerical schemes are mesh independent. So when you have that, at least you are certain that if you have different meshes, so different space configurations, then your results are consistent. Okay, first thing. Second thing, compare with experimental data. So what we have done is try to reproduce a controlled landslide, aerial, not subaquatic, it's aerial landslide. Okay, so this is the same thing of equation that we solved. In blue is the numerical simulation. In black is the experimental one. So what we have captured quite well is the height of the stationary profile, and also, you know, the end of this slide. So here we have some perturbation, but at the end, is quite well reproduced. Now, next thing, try to understand how physical, Next, try to understand how physical parameters change the simulation. So this is the sensibility analysis depending on the most important parameters there. And the most important parameters there are mainly two. One is related with the friction law. That means that the one related with the friction law is the static angle, the static Coulomb angle. And this angle tries to simulate how long this landslide goes away. And this depends on the material, okay? So what we have analyzed is putting different materials, so different angles of frictions, and then try to measure how this angle affects to the wave amplitude in the water layer. And what we have seen here in this curve is that if the ratio of densities, if the angle is small, the blue one, okay, the wave is big because we have more momentum in this sediment layer. So this is transmitted to the water layer, and the wave, the amplitude of the wave is bigger. So this is this kind of figures. Then we have studied how the density of the material related to the water layer affect to the final profile and to the wave amplitude of the tsunami. So if the density, if the ratio of densities is small, then the wave produced, the tsunami wave is bigger. So that means if you have big stones, the tsunami produced by big stones are bigger than the one produced by a material like small sand, okay? We also study porosity and also anisotropy, okay? There are different kind of sensibility analysis that we have performed with this model. And now, a few numerical simulations. This one, in fact, we use 3 different kind of models. At the beginning, this is the initial profile. So here we have the granular material, here we have water. So initially, we use a model to produce this landslide and a water model to produce the movement of the water. But sometime here, in this area, this material is going down, okay? So we use the one that we have, that I have presented previously. So this is a coupling model in order to simulate these processes. We try to reproduce. So here you have, okay, the wave. This is the sediment. It's moving down the slope and produces some kind of sedimentation over there. Okay. So depending on the spatial configuration, we switch from one model to another, okay? Well, this is a test proposed by Heinrich Piatarecci Herbert to simulate some kind of submarine landslide and tsunami. So here you have a material. Well, this is an ideal basin line. So here you have the coastline. Here is the basin. Here you have the material that's moving down to the basin, and they produce, initially they produce a wave that's moving into waves, a positive and a negative wave, and affect to the coastal line. Here I show you a zooming, and this is the wave coming into the coastal line. So here you have reproduced we have reproduced quite well the way where the wave coming into the coastal line. And now are more, let me say, real problem. So we focus in the Alboran Sea, in the Alboran Basin. So we, in fact, we focus in the Alboran Island. Alboran Island is a very small island in this area. Here you have the Occidental Alboran Basin, about 1.5 thousand kilometers, and the Oriental one. And, well, this is a photo of the small island. Okay. And what we have there, they have, the geologists of the Spanish Institute of Oceanography have observed this canyon, you know, this part. And here you have, I don't know if you see that, you have there some sediment deposit. So the hypothesis is that this material, not over, in the past, not over there, is in this area. Something happens to unstabilize these sediments, and a tsunami could be produced in this area. So what we are trying to reproduce is that, okay, the failing of this sediment material in this area, and the mechanism how the tsunamis goes up. Okay. So this is our mesh, computational mesh. Okay. And now our render mesh. In fact, there is no, the resolution over there is not quite high. Not quite high. So this is the why you see that, okay? These flat things. But we haven't much data. But at least in this area, I think it's good enough. So we put it over there. We put it the initial configuration of the sediment. And that's it. Sediment moving down. And there, over there, you see the wave. And, okay, the wave. So one positive and negative wave coming into the this is a very local area. So because the sediment is placed in this local area, then we couple this model with a global one, with a global dealing with the tidal currents and oceanographic currents in the basin. So we could propagate this wave. So first, with this model, we produce this wave, okay, the wave, and then we couple with a whole model of this area to propagate the tsunami. And finally, okay, let me show you if I have time. 5 minutes? Okay. So what we have done is to put this numerical software, visualization tools, meshing tools, etc., in a web platform, in order that our collaborators could use this numerical scheme, these models. So we use this platform to submit computation for different models, visualization, and managing the parallel machine. And I show you a simple problem. So here, suppose you have a channel, okay? And this is the bottom topography of the channel. Suppose that you have the water over there. So this is no tsunami simulation. It's simply a dam break, simple dam break problem. So water is over there. This is topography. So we open the dam, and what we are going to see is to move the water over this real topography. Well, real, not real. It's mathematical topography, not really real. Okay. Okay. So this is our web platform. So I enter to the system. So you have some information about the parallel machine, system, then submit computations, and then utilities, mesh generation, visualization tools, file managing, and also some utils to remote controlling things. So let me submit a computation. So each code, each numerical scheme is associated with a XML file that generates in an automatic way this kind of form. Then we write down all the things. Sorry, some of them are in we change Spanish and English, so this is Spanish. So dump break problem, this is the number of CPU that what you are going to use, depend on the user. That mesh, we could, showing that, we could choose one or another mesh, okay? So we could provide a topography given by a user, this file, okay, then total time, some parameters, so on, so on, so on. Then here, what you could see over there is a simple representation of your channel. Okay, we read the mesh and we give you the information in order to impose boundary condition. And then here, you could put whatever you want. Okay, in that case, is the definition of the bottom path symmetry and the initial condition. Of course, all these things could be done by files, okay? So once you have that, you submit. And now, okay, if you have a user, what you see over there is the load of the parallel machine in order to submit your computation. So now we run the code. Now, the platform is compiling, generating your code, your binaries for your execution, putting in the machine, taking all the files that you want and putting over there. Okay, so that's it. This is running. And now, in order to see what is happening in this simulation, we use some tool based on this client. Here you have our tool, a 3D visualization tool. Okay. Open. Okay. We'll try to give you a view. Okay, say play. That's it. The computation is at the same time, well, the computation is running and you could see what is happening. So what you have here, the water that's moving around these two bumps. Then a shock hydraulic jump is coming down. Then here you have some gray areas, water moving over there. So this water is confined in this part and moving over there. Then here we have also, here we have a closed box, okay? And this is the simulation. Okay, so thank you very much.
Thank you.
Thank you for your very interesting presentation, for your in-depth presentation. I just have one question. You mentioned that you rely on 4 different sources of data.
Yes.
The depth of the ocean, the thickness of the sediment layer, and there are 2 velocities.
Yes.
How should this data be gathered? Should the entire ground of the ocean be observed or inspected?
Okay.
Thank you.
So, the ideal thing is, okay, bottom bathymetry could be obtained from some, well, you know, in order to see the sediment layer is a difficult thing. So, first thing is, in order to have these kind of models, you need some information about how sediments are over there, okay? So, this is not a simple task, and you must pay a lot of money in order to have this information in a, let's say, precise way, okay? But for the ocean part, it's really no problem at all. Because more or less, in coastal areas, we have, at least in the Mediterranean basin, and in fact, also in the close, at least in the problem we are dealing with, close to the Sumatra island, and the information about the bathymetry is quite okay, quite precise, okay? Then we have code to simulate currents. So the enter of this initial condition is no problem. You could take some global code to see that we have previously simulate this time of currents, okay? So we put it, take it from this code and put it in your code, okay? In fact, the difficult part of this model is, here we have the sediment. And what is not introduced in this model is the mechanism of how this sediment that was stable 1 hour before, this became unstable, you know. So what we need to put over there is how, for example, earthquakes could change the stability of this sediment. So for this, just for now, what we have is, we have a configuration. We knew that this configuration is unstable, but it's not really true, because 1 hour before it was critically stable. Okay, so something must be introduced in this model to reproduce from an earthquake, an stabilization of the sediment, and then you could use that. And this is not really a simple problem, because rheology problems is very, very, very complicated. It's very, very complicated. So just for now, what we use this kind of tool, try to measure the risks in areas where there are a lot of sediment in this coastal line, and try to change some physical parameters of the sediment configuration, and try to reproduce how this sediment became unstable, but because we changed the physical parameter. That means the internal friction angle, the ratio of densities, the porosity, okay? So we changed that physical parameter, then sediment became stable, start to moving and generate the tsunami. So just for now is try to play with this model and try to give some kind of information how possible tsunamis in this area could be produced. But for example, if you know, suppose that you haven't, you have some information on how the bottom topography changed, then we put it, with this data, we put it in, not this model, but in other model that we have developed. So you have a really some data of how this bottom topography changed, and then we could reproduce the wave, the water wave of that, of the tsunami. But again, this is not a very, these data are very complicated to obtain. So.
Thank you. Very interesting. Have you had the opportunity to compare your model data with actual observations of local tsunamis, local landslide?
Okay, we're trying to reproduce the Papua Papua tsunami, and then we have also some data in the local in the Sumatra area, and we try to reproduce that with our model, but it's not finished. Okay, and another thing that we are trying to do in collaboration with engineers is try to reproduce controlled tsunamis in the laboratory by changing with some mechanism, the bottom topography. So, for example, you could put a piston modeler and move it inside the water. So this is we try to compare with this kind of controlled experiments.
Any other questions? If not, thank you very much for coming. Thank you to our two speakers and for being accommodating with the missing speaker. Thank you very much. And thank you for the audience for the interesting questions. See you after lunch, maybe.